So before we define an inverse function formally, I think it's much more useful for us just to understand intuitively, informally, what it means. So informally, the inverse of a function f of x undoes the work of f of x. Now, to a mathematician, this definition, I haven't even given it the name definition. It is completely unsatisfactory because we don't know what the word undoes means and we don't know what the word work means. But this is just going to be our initial idea of what an inverse function does. And you can start counting now how many times we're going to use inverse functions this semester. There are going to be a lot. This is a really important and very useful concept. So we have some notation for inverse functions. We denote the inverse, and this is if f has an inverse function. We'll talk later about whether f does or does not have an inverse function. But the inverse function, if it exists, of f of x is denoted, and we were talking earlier tonight about the importance of good notation. Some people don't like this notation. It is denoted f superscript minus 1 of x. And we read that f inverse of x. Now this week we've already seen a superscript minus 1, and it meant something different. So this is a very important warning. And the warning is that f inverse of x is not the same as 1 over f of x. That is to say, the word inverse is not synonymous, does not mean the same thing as whatever this word means. And what this word means is you take the reciprocal. So inverse and reciprocal are completely different things, as we will see in the very next example. If you want to write 1 over f of x without using a fraction, what you need to write is f of x in brackets to the minus 1. This is a reciprocal. It's the same as saying this. This is inverse, completely unrelated to reciprocals. Let's do an example to make this all clear. So find f inverse of x for each of the following f of x. First f of x equals x plus 3. I guess I really like the number 3 today. X plus 3. So the job of this function is that whatever you feed it, it adds 3 to it. The inverse is supposed to undo that. So that means ask yourself, how do you undo the work of adding 3? And I hope you're answering nothing to do about dividing or taking a reciprocal of all. I hope you're saying that the way you undo adding 3 is by subtracting 3. So f inverse of x here is x minus 3. And notice that looks nothing like 1 over f of x. We're not doing any dividing at all here. And let's just do an example with some numbers to see how this goes. So suppose I do f of 5. F of 5 is 8. Suppose I now do f inverse of 8. F inverse of 8 is 5. F inverse has done its job. The job of f inverse was to undo the work of f, and that's exactly what happened. If you feed 5 into the f function, you get 8 as the answer. Then you feed 8 into the f inverse function, and you're right back to where you started at 5. F inverse undid the work of f. We did nothing with reciprocals at all there. How about f of x is 4x? So this function's job is to multiply by 4 whatever you feed it. So what should the inverse function be? That should be dividing by 4. So x over 4. Now I was saying this isn't a reciprocal. Is this a reciprocal of this? No. The reciprocal of 4x would be 1 over 4x, meaning the x would be on the bottom. But that's not what we've done here. If we were just to try an example, f of 7, 4 times 7 is 28. And then I take f inverse of 28, and I get 7. That's confirming that F inverse is doing what it's supposed to do, namely undoing the work of F. These functions had inverses, but we said that not all functions do. So does f of x equals x squared with a domain, remember the domain is the set of values that you're allowed to put into the function, so with a domain of all reals, all real numbers, have an inverse function. There's something called an inverse relation, which is a much more abstract thing that we're not going to worry about here. We're asking, does this have an inverse function? Think about what the graph of f of x looks like. It's just your favorite parabola. We've seen it earlier tonight. So, for example, if I plug in 3, I get a y value of 9. If I plug in negative 3, I also get a y value of 9. So f of 3 equals f of negative 3 equals 9. So then the question is, what's f inverse of 9? Because f inverse is supposed to undo the work of f. So I know that sometimes when I get an answer of 9 from f, the input was negative 3. But other times when I get an answer from 9, an answer of 9 from f, the input was positive 3. So can I say f inverse of 9 could be 3 or it could be negative 3? What would be the problem with doing that? The problem with doing that goes back to our definition of function at the very start of the night, which is that each input, if we're going to have a function, should only have one output. So I'm not allowed to say f inverse of 9 is sometimes 3 and sometimes negative 3. So if we have the domain here with all reals, this is the f inverse does not have an inverse function. So this f has no inverse function. Now, I know a lot of you are thinking, well, what about the square root function? Isn't that the inverse of the squaring function? It is, but we have to restrict the domain. So if we restrict the domain of this f, of f equals x squared, f of x equals x squared, and this is one of the things the whole world has pretty much agreed. Rarely does the whole world agree on anything, but this is a case where the whole world really has agreed. If you ask any calculator on the planet, what's the square root of 9, what do they all tell you? They always tell you 3. They never tell you negative 3. You can try it. Ask your calculator what the square root of 9 is. Ask your friend's calculator. They always say it's positive 3. So if we restrict the domain of f of x squared to the non-negative reals, then f does have an inverse function. Because then I'm ignoring this whole side. This is all gone now. And when that happens, there's no danger of getting the same y value from two different x values. The problem before was that both x equals 3 and x equals negative 3 gave me the same y value of 9. Now there are no duplicate y values happening. And that's the square root function. So this is why we can write f of x equals square root of x. This is a true function, has only non-negative outputs. That is to say, the square root of 9 is always 3. It is never negative 3. All around the world, always positive 3, never negative 3. Because we want the square root to be a function. Otherwise, you could ask your calculator what square root of 9 is, and it would say 3, and your friends would say negative 3, and that would be a mess. Now, we need to contrast this with something else, though. The solutions to the equation see, now I'm not talking anything about functions. I'm just saying I've got an equation x squared equals 9. Find all the x's that make this true. Those are x equals 3 and x equals negative 3. So take a minute to think about that. Solving an equation like x squared equals 9 is very different than evaluating the function f of x equals square root of x. This is a function. For each input, there should be exactly one output and no more. All right. So the fact of why we were able to make this a function is that this f, when I restricted the domain, this f became what is so-called one-to-one. So a function f of x will have an inverse function if f is 1-to-1. And the sort of informal way of defining 1-to-1 is that no two x values give the same y value. So in order to make the square root function, we needed to make f 1-to-1. We needed to remove all the negative x values so that we didn't have any repeat y values. We'll have to do the same thing next week when we find inverses of trigonometric functions, because they have the same problem that x squared does. They have repeated y values for the same, more than one x value will give the same y value. So now I think we're ready to make our actual definition. So let's suppose that we do have a function f of x that's 1-to-1. Then f minus 1 of x is the inverse of f of x if, and then we want it to do what we did up above. We want f inverse to undo the work of f. So if whenever we have f of a equaling b, we also have f inverse of what equaling what. So if you think back to the examples that we did before, we had f of 5 equaled 8, and then f inverse of 8 equaled 5. So we also have f inverse of b equals a. So that's our definition, our formal definition of what it means for what it means to be the inverse of a function. But it's very useful to have both in mind this formal definition and the informal one that we started with, namely that f just undoes the work of another function. So let's try one example here. So let f of x be x cubed. Now you should stop and think to yourself for a second about whether I need to make any domain restrictions here. And I don't, because the graph of f of x equals x cubed just is increasing the whole time for all real numbers, meaning there are no y values that appear more than once. So this f is 1-to-1. So let's evaluate the following. So f of 4, it's not too hard. We just plug 4 into x cubed, and we get 64. And then f inverse of 64, we know that's supposed to undo the work, so that should be 4. What if I then do f of f inverse of 64? So f inverse of 64 is 4, and f of 4 is 64. So the thing that I put into f inverse, and then I take that output into f, I end up with exactly what I started with. And it should go the same the other direction as well. F of 4 we know is 64. And f inverse of 64 we know is 4. So each function is undoing the work of the other one, whether we do f of f inverse or f inverse of f. And we'll have to be a little bit careful when we write this out in general for about domain and range. But for right now, what we'd like to do is think about how the graph of f inverse relates to the graph of f. And we have an applet for you to experiment with to try to come to a conclusion about that. So please explore with that, and then we will come back and talk more about inverses.